Hello and welcome everyone to this edition of MIT Abstracts. We are so excited to have you all here. Welcome to the incredible Nord Anglia students who have been with us for this series. Welcome to their fantastic teachers, and welcome to some parents who might be on with their students right now. We are so excited to have you here. We have an amazing MIT abstract lined up for you today, and I am absolutely brimming with excitement right now. I'm your host, Fatima Husain. I'm a graduate student in the MIT Department of Earth, Atmospheric and Planetary Sciences, and I study ancient Earth. And I'm especially excited for this abstract today because it's originating from my own department. So we're showing you something that falls within this realm today in planetary sciences. So just a quick explainer on what an abstract is. So some of you who may not be familiar with the name, an abstract is actually just a snapshot of a research paper or a big body of research. So it's just a quick summary. It's just a small, a few sentences describing what you're going to see. And what we're doing with this series is we're bringing an abstract of an amazing, inspiring person from MIT straight to your screens. And that brings me to introduce our incredible speaker for today, our expert. He is a really great inspiration to me, a big role model. I'd like to introduce Professor Binzel from MIT today. Hi, Professor.
Good morning, Fatima, and welcome everyone. It's a real pleasure to be here, and welcome to MIT in this virtual way.
Fantastic. Okay, Professor, I'm going to let you take it away, and you're welcome to share your slides.
All right, let's see if we can make this work. And I think it does. Isn't technology amazing? So welcome everyone. I am going to give you sort of a sampling. Think of this as a buffet or a smorgasbord. And I'm going to give you a sampling of some areas of space science that I do. And the reason why this is so exciting to me is it doesn't seem like it was that long ago. I was sitting in your chair. I was a curious young kid who just loved space, and how I got to do and be what I have been able to do over the years is because I stayed curious. I always followed my curiosity. I never let my curiosity rest. And if this is something that you're passionate about, or whatever you're passionate about, don't let your curiosity take a day off. Stay curious, stay focused, and go for your dreams. And that, I think, is a great recipe for almost anything you might want to do. So, as the title might have advertised, I'm going to talk a little bit about asteroids. I do a lot of work in studying asteroids. And this is probably the picture you have when you think asteroids. You think Star Wars and the Millennium Falcon. And, this is really great Hollywood, but the real asteroid belt, it really isn't anything like this. So don't learn from the movies. Learn from real books. And, these places called libraries and things like that are wonderful resources. Um, Anyways, it turns out, just as a matter of fact, that space is, even though there are millions of asteroids out there, space is so enormous that the average spacing is about 1 million kilometers between asteroids. So driving a spaceship out through the asteroid belt is really not a problem at all. It just makes for good science fiction movies. So speaking of the asteroids, where are they? And I'm going to have a few questions in here. So you might get ready in the Q&A window to type an answer. And I've got a question for you coming up. But I'll answer this first one, like, where are the asteroids? And it's kind of fun just to give us a little reminder of what our solar system looks like. And this is just the inner part of our solar system, where you probably know Mercury is the closest planet to the sun, then Venus, and the third one out is our favorite, Earth, followed by Mars. Mars is going to be in the news very soon. Keep close watch on Mars and all this spacecraft arriving at Mars over the next week or so. And then we go from Mars out to Jupiter. And it seems like there's this empty space between Mars and Jupiter. And this is what we knew until about 200 years ago, when the first asteroid, an asteroid named Ceres, was discovered between Mars and Jupiter. And that was just the first of many. And right now we know, in terms of fairly sizable objects, there's more than 700,000 known asteroids in this region between Mars and Jupiter. And it's just sort of blown up in this diagram here. So anyway, that's the first question. Where are the asteroids? And they're mostly between Mars and Jupiter, but not all of them. You know, sometimes Jupiter's the biggest planet in our solar system, and its gravity will nudge and tug on the orbits of some of these asteroids and cause them to become sort of elongated in shape. And those elongated or eccentric orbits start going across the orbits of the planets like Mercury, Venus, Earth, and Mars. And sometimes those asteroids hit a planet. We know when they hit a planet or a moon, they make craters. And we see lots and lots of craters on the moon. And that's because the moon surface is very, very old. 4 billion years old, and it doesn't have weathering processes and things that erode the surface and change its surface over time like the Earth does. So the moon is recording a really interesting long history of our solar system. But you know, sometimes these things do hit the Earth. And in fact, an enormous asteroid hit the Earth 65 million years ago. And we think the consequence of that, all that energy from that impact, was the end of the dinosaurs. It affected our climate so much that species like dinosaurs did not survive. And so, you know, in some ways that's good news because that meant the mammals could arise. So it was kind of good news for us, bad news for the dinosaurs. But in terms of this as something to worry about, these things are extremely, extremely rare. And it's something that's great to understand, but not something we worry about on on a daily or nightly basis. All right. So now here's my first question. So get ready to type. The question I have is, you know, sometimes small pieces of asteroids fall to Earth, and this happens a few times per year. And if we can collect those pieces, we can analyze and study them. And so my question to you, if you're ready to type, what do we call these small pieces of asteroids that fall to the Earth and end up in our laboratories or museum?
We have a couple of students in the chat saying meteorites.
Let's see. They are indeed meteorites. So meteorites are things that we study. And the reason why, as scientists, we are so interested in meteorites and asteroids is because these are leftover pieces from the very beginning of our solar system, 4.5 billion years ago. And we want to know how planets and solar systems form, because not only do we have our own solar system, but we know there are planets around many, many thousands of other stars out there. And so nature is forming planets everywhere. And this is our chance to study how it works up close. And that's why it's so exciting, because what we can learn here, we can apply to the universe. It's just amazing. I've been doing this for an entire career, and I still think it's amazing. And that's why I say keep your curiosity, stay with your curiosity, never give up on your curiosity. All right. So here's a question, and I'll answer this one, is what do asteroids look like? Well, you know what the moon looks like. You can go up at night, out at night, and the moon will be back in the evening sky in a week or so. And you can go up and go outside, and part of your curiosity is just looking at the moon and kind of watching where it is from night to night. That's a way of being curious. And so the moon you're familiar with, but what do asteroids look like? Well, the largest asteroid, the one we talked about before, named Ceres, is about a third the size of the moon. That means that Ceres is about 1,000 kilometers across. And the first time we ever saw Ceres was with a NASA spacecraft called the Dawn mission. And the Dawn mission went to the two largest asteroids, Ceres and another asteroid about half its size named Vesta. And we're going to zoom in on Vesta. So this asteroid we're zooming in on is now kind of is Vesta itself. But every time we go to an asteroid, we can now see that there's more and more smaller asteroids because there are more small asteroids than big ones. And so we're going to kind of do a kind of a size comparison walk through asteroids that we've seen by different spacecraft. So here's Vesta, and then a series of other smaller and smaller asteroids. And maybe if you're curious, you notice that as you go from big asteroids, which are kind of round, to smaller asteroids, they get more oddly shaped, more potato shaped even than the big ones. And that's because the largest ones have so much gravity that gravity can pull them together almost into a spherical shape. And as you get to smaller and smaller sizes, they just look like irregular rocks. And you can almost see this walking down a stream bed. So you can be curious just looking at rocks in a stream bed and thinking about what rocks in space are like. And you can see how your curiosity can take you anywhere. It's really a wonderful, wonderful thing. So we're going to zoom in on this asteroid named Lutetia, which was seen by a European spacecraft called Rosetta. So the big one in this picture is Lutetia, the one we just saw, the little tiny dot a minute ago. And we see more and more oddly shaped, sort of potato-shaped, smaller and smaller asteroids. And there's this one little tiny dot here that we'll zoom in on. And this is an asteroid that's half a kilometer across, 500 meters across. Its name is Bennu. And this is what Bennu looks like up close. It's just sort of a big collection of rocks and rubble. It's probably a small asteroid that's been battered together by collisions with other asteroids, and it barely holds itself together by its own gravity. And 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 this asteroid is getting into a size that we can almost kind of comprehend in the scale of our own planet, our own cities. This asteroid Bennu at 500 meters tall is as tall as some of the tallest buildings, tallest structures that you might be familiar with here on Earth. So it's interesting that we can send a spacecraft to something that's sort of a building sized object out there in space. And in fact, we have sent a spacecraft there. And in fact, I'm part of this mission. I'm part of 4 NASA missions that I've gotten to be to participate in and contribute as a scientist to. And this is the one that's the most active right now. It's called the OSIRIS-REx mission. It's a NASA mission to the asteroid Bennu that we launched in 2016. And I'll tell you about what we're doing with that mission in just a moment. You can see our spacecraft there on the right. It's kind of an odd shaped spacecraft, almost looks like a mosquito. And there's a reason why it looks like a mosquito. But first, I want to talk about something really special about MIT and the OSIRIS-REx mission. And that is, imagine you're sitting in a class. And you can see in our class, we have men, women, diverse people from across the world in our classroom. And imagine going to school and getting to design a space experiment. And that's what we did in this class at MIT. And in fact, we spent about 10 years designing and building a space experiment called REXIS, which is a regolith X-ray imaging spectrometer. And it's a fancy name for an instrument that's designed to tell us what the chemistry is of the asteroid's surface. Anyway, so these are our students hard at work building this instrument. Some of the students in there on the left are Pranoy, Laura and Mark are in the middle, Connor's on the right. Anyway, just a really great group of students that helped put this together. There's our student Mark Chodas and our lead engineer, Dr. Becky Masterson, putting the finished product on board the spacecraft. There it is. That's the OSIRIS-REx spacecraft ready to go to the launch pad. We get the spacecraft onto the launch pad, put it in the rocket, and off we go to out to outer space, launching from Cape Canaveral in Florida. And how fun it is to build something and go down to Cape Canaveral and watch it launch. All right. So we arrived at Bennu. It took about 2 years in space to get to the asteroid Bennu. And once we got there, that thing that looks like a mosquito on the proboscis at the end of the spacecraft is actually kind of like a vacuum cleaner. And we wanted to go and get a sample of this asteroid because this asteroid is rich in carbon chemistry. And we know that from our telescopes here on Earth. And so we'd like to go get a sample and bring it back and study it as a fresh meteorite, but it's a meteorite we went and got, not contaminated at all by anything on Earth. And so we successfully sampled the asteroid with this funny sampling mechanism back in October last fall. And you're seeing the video over and over of the sampling process. We kind of made a mess when we fired the gas to generate the little vacuum cleaner mechanism to get our sample. But anyway, the asteroid didn't care. It was very nice. We think it has a great sample. And so we are about to fire our thrusters next month to send us on a path back to the Earth. And that sample will come through the atmosphere, parachute to the ground in 2023. And so with that, I'm going to stop. That's just a quick abstract or snapshot of different things in working in space and working on asteroids. And maybe you've got lots of questions for me. So I'm going to stop the share of the screen, and we'll let Fatima take it away with your questions.
Yeah, you were completely right, Professor. We do have a lot of questions for you. And to start us off, we have a question from Alexander from Nord Anglia. And Alexander's wondering, how fast does an asteroid move?
Oh, wow, that's a really great question. So in their orbit, they go about 20 kilometers per second. In their orbit around the sun, and relative to one another, they kind of pass each other at about 5 kilometers a second. And if they come close to the Earth, they kind of go past the Earth at around 20 kilometers a second, maybe 30 kilometers per second. So anyway, it's a great question.
And we have another follow-up question from Marion. And Marion's wondering, how rare is it for an asteroid to hit Earth?
Yeah, so fortunately, it's very rare. Small things hit all the time, and we collect several tons of dust every day. And those are little tiny meteors that you might see at night. A meteorite, something big enough to survive through the atmosphere and give you a sample, happens a few times a year. But maybe once every few hundred years, we get something like Tunguska in 1908 was a large impact that flattened a bunch of forest in Siberia in 1908. There was something about much smaller than Tunguska, but very fantastic to see over Chelyabinsk, Russia, in 2013, and that gave us some samples as well. So for things that are of any particular size, it's typically hundreds of years, and things that are, I'll say, seriously damaging is on average millions of years. So these happen, but it's very, very rare.
So you're telling me that these smaller meteorites that come and visit us on Earth, are you saying that perhaps Nord Anglia students and I could go and look for some someday?
Yeah. Yes, you have to be a little bit lucky. A lot of rocks end up in my laboratory that people find, and because they look a little unusual, but they're almost never happen to be meteorites. But there are places in the Sahara Desert where if it's sand dunes everywhere and you find a rock in the sand dune, there's a reasonable chance it's a meteorite. And the ice sheets of Antarctica are another place where if you just see a rock sitting there on the ice with nothing else around it, most likely it came from space.
All right, Nord Anglia, you know where we're going next, the Sahara and Antarctica. So bundle up, it's going to be cold. Um, we have a student who's wondering, I think they really enjoyed your opening slide, but they're wondering, are there any similarities between the way asteroids are depicted in movies like Star Trek and Star Wars versus real life?
Maybe just the odd shapes. I think there's even one tennis shoe shaped asteroid in the in the Star Wars scene. You probably can read about that on the web. Um, Other than the fact that they're irregularly shaped, I think that's about the only thing Hollywood gets right on this one.
Got it. And we have a question from Daniela, and she's wondering, does the size of the meteor affect how fast it reaches us at Earth?
Oh, that's a really interesting question. So in space, velocity is velocity. There's nothing to slow you down. There's no friction to slow you down in space. Um, uh, so mass doesn't matter in terms of your orbital velocity in space. But if you're coming in through the atmosphere, if you're small, then the atmosphere, if you're an object coming in the atmosphere, if you're small, then the friction of the atmosphere might be so intense and generate so much heat that it vaporizes you. So it protects us from small objects. If you're sort of medium sized, I'll say the size of a school desk or a school bus, the atmosphere slows you down quite a bit before you can reach the ground. And if you were something the size like 10 kilometers across, that we think was the end of the dinosaurs in the late Cretaceous, then you're so big that the atmosphere doesn't matter. It's like dropping a big rock in a mud puddle. The water in the mud puddle doesn't much matter.
Got it. And we have a student here who's particularly keen on asteroids, and they're wondering, what inspired you to study asteroids and not other space things like galaxies or planets?
Oh, well, thank you for asking that question. I a lot of reasons why I wanted to study planets, and that is because I got to see the Apollo missions as a kid, and so that fascinated me. That I understood that the moon was a very fascinating place all by itself, and I had a telescope as a little kid, and I loved seeing Saturn. I saw Saturn and Saturn's rings, and I was so captivated by it. I said, "Wow, our solar system is so interesting. I don't have to leave my backyard." To be a space scientist. But another thing that led me to study asteroids and planets was that these were places that I thought I could go someday. When I was a kid, we had never launched, we never basically even launched a satellite, not alone humans into space. And I said, what can I study as a kid that I can go do myself someday? And I said, well, I'm never going to be able to go to another galaxy, but I could go to the moon or I could go to Mars. And I could send spaceships to places like Pluto, which I've done. And so I think I kind of had this grasp of how far could my imagination go and my mind and hands follow in the timescale of a career. So I think that kept me always in our own solar system, because uh, um, for me, when I have curiosity, I want to get to the answer. And I'm not sure I'll ever get to the answer about exactly everything that galaxies are or black holes are. But maybe I'm getting to a lot of answer about what asteroids and meteorites and planets are.
Got it. And now one of our students is wondering, how many asteroids have you discovered? They're guessing four.
Oh, yeah, I think you can look up on Wikipedia and find four or something like that. One of them I named after my grandfather, um, who inspired me. So here's to all those grandparents out there that my grandfather inspired me, and he was kind of, I think, planted the idea that think about things you can explore and do, and you can see happen in your life. And he remembered Lindbergh. He was a young man at the time of Lindbergh, and he was born around the time of the Wright brothers, and he lived to see Apollo. And so he was an amazing generation of going from the Wright brothers, a generation that saw everything from the Wright brothers to Apollo. So anyway, the first one I discovered named after my grandfather, who inspired me, and my spouse, my wife, has one, and a few other names there that I got to choose.
That's really sweet and meaningful. That's wonderful. And now students are wondering, I think partially inspired by your hat and the fact that you've worked with four NASA missions, but could you tell us a little bit about your work with NASA? How did you even come to work with them in the first place?
Yes. So my role in these NASA missions is as a scientist, largely, and now lately I'm building things to put on the spacecraft. But the things I'm building are designed to get scientific answers. Um, So I got involved because because I was driving the science. In other words, I was making telescopic observations of asteroids, trying to find interesting places to go, like this carbon-rich asteroid Bennu. And so when we started, scientists started, or an engineer started designing a mission to go get a piece of a carbon-rich asteroid, they said, "Well, who's the expert on carbon-rich asteroids?" I said, "Okay, sure, I'll come along and advise you." So you just do what you do. You follow your passions. You try to be really good and really expert at what you do. And so the missions kind of followed. And I was studying Pluto as a graduate student, and when we started being able to design a mission to Pluto, I was one of the handful of Pluto experts on the planet. So it was very natural to join in. So just follow your curiosity, just try to be good at what you do, and these things sort of follow. And then the job I do is really trying to design the cameras, the instruments, thinking about what science questions do we want to answer when we go there, and how do we design our cameras, our instruments, to answer those scientific questions. So I try to define the science so that the engineering can address the science, and it's a very interesting intersection between asking scientific questions and finding engineering solutions that can answer those scientific questions. And that's where I spend all my time, trying to think about the science, and then how can we make measurements to answer the science questions.
Oh, that's fantastic. And that seems like a very interdisciplinary skill set that you have to develop, right?
You do. So, but you start somewhere, and I started as a scientist, and I never really thought about building space instruments and things like that. I was always curiosity driven, and eventually your curiosity takes you to the point where if I don't start building and designing the instruments to answer the questions, no one else will. And so as a scientist, you get to the point where you say, "Oh, the heck with it! I've got to do the building and designing now to get the answers."
And so, Professor, we have a very interesting, I think, very future thinking question. But one of our Nord Anglia students, actually, I think a couple of them are wondering, can we get, valuable minerals or metals from
Oh,
asteroids?
what a great question. So we have a mission. I'm part of a mission called Psyche. This is a mission that will launch in about 18 months. And it goes out into the asteroid belt. There's a large metallic asteroid in the asteroid belt named Psyche, named after a Greek, one of the Greek muses. And we think scientifically, we think Psyche is the core. You know how you may know that Earth has an iron core, and small planets, when they form, if they form in a molten way, the iron goes to the center, and then it's cooled off. And we think that Psyche is the core of a small planet that once existed in the asteroid belt. So if we want to know what's on the inside of a planet, we can go there and look. That's why it's so exciting. Um, but there it is the metals in the middle of the asteroid belt, and you can read news stories about how many $1 trillion the metal is worth. Well, that's only if you can bring it back and get it to Earth and market it, do something with it. So it's a little bit of hyperbole to talk about the value of minerals and the metals in space. I think that what might be the first thing that might be valuable in space as a space resource, if you will, is just simply water. Because if you're astronauts get thirsty, we all get thirsty, and astronauts in space get thirsty, and you either have to bring the water with you, or if you can find it at the poles of the moon, or some of these asteroids have water in them. Then you can extract it while you're in space, and you don't have to bring it with you. So I think water will be the first real space resource that will be part of the what I call the space economy of the 22nd century.
Wow. Okay, that is a lot to think about for sure. And I think we have these future resource experts. I think the gears are turning now in their heads. Um, we have a student who wants to ask a really lovely question, in my opinion. Are there any asteroid mysteries or things that have just continued to be elusive that you'd like to know about?
Oh, wow. What a great question. I like to know how they're put together on the inside. I think we can see them on the outside, and now I'm curious about how they work on the inside. Are they just intact like solid rocks on the inside, or are they really just totally fractured and just barely holding them together by their own gravity, which is something that we sort of think. And I'll tell you a reason why I'm so curious about that is I do think about the problem, if you will, or just the reality that asteroids do pass by the Earth from time to time, and there's always stories about them, but they're really just anything anywhere that just generates a little meaningless news story. But over time, I think, over time scale of centuries, this sort of thing we really ought to understand. And so I think, so I'm curious about how they're put together on the inside, because if we ever had one that was posing a hazard to us and we had to go out and push on it, we'd kind of like to know how it holds itself together. So if we push on it, we know that we can do it in an effective way. So I'm curious scientifically about how they're put together. But I think it's very practical to know how they're put together too.
So you kind of mentioned something that a lot of students are asking about, and they want to know, I mean, can we stop an asteroid if we know that one's coming towards Earth and we don't want it here? Do we just push on it? What do we do?
Well, the most important thing we can have is time. And this is why I think the most important thing we can do is just discover them. And I've been advocating for a specialized spacecraft, something called the Near Earth Object Surveyor mission that NASA is just on the verge of funding, and they never can quite decide that it's a high enough priority to do. But I think the first objective is we need to do the best job we can of just finding what's out there and knowing all their orbits and making sure that there's nothing that's headed our way any time in the coming century or centuries. But if we did find something that was going to be a hazard, and say in 50 years from now, having 50 years is really great. You're having a lot of time to think about it, to understand the object, understand how to push on it. And do we attach rocket motors to it and push on it? Do we use a solar sail to kind of drag it? Do we hit it? Do we, go and punch it and try to knock it off course a little bit? And then lots of different ideas. There's even going to be a little test mission, something called DART, the Double Asteroid Return DART. I can't remember the acronym. I'm sorry. Acronym DART, DART mission. And we're going to test by firing a little projectile into a tiny asteroid and see how it moves. And so we're just learning how to do it. But the most important thing is just having lots and lots of time so we can try different things if we need to.
I'm trying to picture an asteroid with a sail on it now. That sounds pretty cool.
Yeah, anchor it with a giant solar sail or something. Anyway, there's as many ideas out there as there are. No, there's 10 times more ideas out there than there are scientists. And you can bring your own. So anyway, it's an open question. It's an ongoing question that we're still giving a lot of thought to.
Honestly, that's super cool. And now I think we have some future space travelers in our midst on the call, and they're wondering if they wanted to visit the asteroid belt.
Uh-huh.
How cold is it there?
Oh, how cold is it there? Well, it's colder than the moon, and it depends whether you're in the sunlight and it's colder than Mars, and it depends whether you're in the sunlight or on the dark, the nighttime side. But it's well below 0 Fahrenheit, and minus 30, minus 50 centigrade on the surface of an asteroid. So bundle up. You'll need a spacesuit.
Okay, I'll let them know. And some of these same students are wondering if they manage to land on an asteroid, is there enough gravity to hold them down?
Oh yeah, you need to tether yourself down. It's almost like being in floating around in space. There's so little gravity there, and you'd have to anchor yourself down. I've thought about. I've never got. Maybe one of you guys will take this idea. Think about the little underwater Jason robots that have explored the Titanic and things like that. I've thought of designing a little in space, almost like a spider kind of a free floater. And so the astronauts don't go to the asteroid themselves, but they send their little Jason vehicle over, and it has lots of arms to it, and it can kind of anchor itself and then use another arm to scoop up samples and bring them back to the spaceship. Because asteroids they're rocky and craggy. They're probably not very friendly to a spacesuit. They're going to get dust and debris and all the joints and gears of your spacesuit. And so I'm not sure an astronaut really wants to go roll around on an asteroid sandbox. Um, think of the Peanuts character Pigpen and all the dust that's always around that guy. I think an astronaut at an asteroid would be like that Peanuts character.
Got it. And now we have some students, they're very interested in your Pluto expertise, and you gave us a wonderful tour of the solar system. They're wondering, what makes a planet and what makes a dwarf planet a dwarf planet?
Oh, great. So Pluto is a dwarf planet, and as I like to say, dwarves are planets too. So Pluto is a planet in my heart, and I think of our solar system having about 15 planets. When you think of Pluto and Eris and Maki, some of the asteroids out in the Kuiper belt, there's a whole nother asteroid belt to our solar system out beyond Neptune. That's called the Kuiper belt, and Pluto happens to be part of the Kuiper belt. So really what makes a dwarf planet is something that's big enough to hold itself together into a sphere by gravity. So Ceres, the largest asteroid, is actually a dwarf planet. And so it's really, astronomers have their own categories, but I say the heck with what astronomers think. It's really, what does the planet think? And if something is big enough and nature is able to, and nature says, I'm big enough, I can pull myself into a sphere, then you're a planet or a dwarf planet, and you're a planet all the same.
I think that's a really good take-home message for these students about dwarf planets. And now we have a student who's wondering, they listen. Some of these Nord Anglia students were on one of our earlier MIT abstracts where we talked about tests and discovering exoplanets and how that works. Can we discover, asteroids outside of our solar system using the same technology?
Oh, wow, what a great question. Well, we can't see them as individuals, but sometimes we see them as a temperature. And we found that we actually know there are asteroid belts around other stars because we see the heat signature, or sort of the glow of these exozodies, or sort of dust clouds and debris clouds and asteroid belts. They kind of give an extra glow to the star that's not the same as the kind of heat signature that a planet gives. And so we do know that there are asteroids and Kuiper belts around other stars. So yeah. So again,
Wow.
another reason to study our own, because it's part of how we learn more about many other places in the universe.
I think that if one of these Nord Anglia students discovers one of those asteroids, I think they should name it after this series, MIT Abstracts. Do you think that sounds good? Would that be a good name, Professor? Fantastic. And now we have a student who's wondering, and I think they're inspired by your photo of the moon that shows a lot of craters. I mean, um, after these craters, hey, can we use these craters to tell us more about that planet? Does it tell us about the composition of a moon or a different planet, or can it tell us about ages? What information can we get after we have that crater?
What a great question. So there's something called, you can do this. It doesn't sound very exciting, but it's actually very scientifically rich. It's called crater counting, and you can think of a planetary surface, if it sits there for a really long time and nothing else happens to it other than things hitting it, then an old surface of a planet has lots and lots of craters, and a young part of a planet has very few craters. And in fact, the moon is perfect for this. And even with binoculars, you can look at the moon and you can see parts of the moon that are heavily cratered, and then the flat plains, the seas, like the Sea of Tranquility on the moon, has almost no craters in it, and that's why Apollo 11 landed there. Very smooth. But the reason why it has almost no craters is because the Sea of Tranquility is actually a lava flow that's much more recent than the old cratered parts of the moon. And so just by looking at the relative number of craters you see in one part relative to another, you can get different ages. So craters are incredibly useful tools.
Got it. Yeah, that's really exciting. We have a student who's thinking of meteorites, I think, and they're wondering what exactly is a meteor shower?
Oh, a meteor shower is when, usually when the Earth travels through the tail of a comet, and comets give off the ice and dust, little tiny dust particles. And so, if we happen to go through a place where we're in the tail of a comet, then we got lots of these dust particles, and you just see lots of little meteor streaks per hour. You might see 10, 20, or 50 little meteor streaks per hour if you are in a really dark place and you're kind of up late after midnight, get permission to stay up and watch a meteor shower. So it's just a place where we're going through a little dust cloud in our solar system. Usually it's the former tail of a comet.
Oh, that's super cool. I hope I get to see a meteor shower one day. I see them on the news sometimes, people mention them. So now we unfortunately have to start closing, but I wanted to ask you one closing question. So we have a lot of students who I think are probably going to be future astronomers or planetary scientists or even astronauts on this call. What are some skills they should start working on today? What are the good qualities of good astronomers and planetary scientists?
Well, the number one is quality is curiosity. Let your curiosity drive you. Determination, curiosity, determination, persistence, and a little bit of skill at math and science is good too. But I was never the best math student, and I was never the best science student, believe it or not. But I was determined, and determination, persistence, and grit mixed with an unending curiosity is the best recipe. So, and I think all of that's within all of our capabilities. So keep that curiosity, keep your drive, keep your determination.
That is fantastic advice. And now I have to quickly share a screen to tell our amazing students on the call what we have coming up next. So if you enjoyed today's MIT abstract with the incredible Professor Binzel and all the asteroids he told us about, you might enjoy our next MIT abstract on a journey through mathematics with John Urschel, and he's a graduate student in the MIT Department of Mathematics. So I'm really excited to see you all there. And before we say goodbye, I just wanted to extend a sincere thank you to Dr. Rick Binzel. Professor, thank you so much for sharing with us your insights and inspiring us. I think we have a lot of students who are going to be curious and determined from here on out and
Perfect.
apply that. So one day we'll hear an abstract from them, I hope. And thank you so much to the students who asked us, oh my goodness, over 1,000 questions this time. I can see the numbers are still going up. Oh my gosh, you guys, this is incredible. We had some wonderful questions. Thank you to the Nord Anglia students and their teachers, and thank you to the parents who have joined us for tonight. And I wanted to close by thanking Nord Anglia for making the MIT-Nord Anglia collaboration possible, for giving us the opportunity to bring this wonderful series and wonderful experts like Professor Binzel straight to the screens of Nord Anglia students around the world, and for allowing us to share science with everyone. So thank you all. And once again, thank you so much, Professor. I think students had a blast.
Thank you. Me too. And it's a thrill to be with you guys. Stay curious.
Fantastic. All right. Goodbye, everyone.